Australia produces about 20 million tonnes of wheat annually. Of this, 1 million tonnes are used by the domestic milling industry. Wheat arrives at the mill by road and rail. The grain is unloaded and held in storage bins until required. Before wheat is milled, all impurities are removed. Magnets are used to remove iron and steel. Milling separators are used to screen out large impurities such as sticks, large seeds and pieces of string. Small stones are removed by the dry stoning machines. The wheat grains are lifted off the screen by an upward air current and recovered. The stones, being denser, progress up the screen and overflow into a container. Foreign seeds are separated from the wheat by disc separators. The rotating discs have concentric rings of specially shaped pockets on both sides of the discs. Seeds the same size or smaller than the pockets are lifted from the grain bed and discharged separately. With small pockets, small seeds and broken grains are removed, leaving intact wheat and large seeds behind. Then, with wheat-sized pockets, the wheat is removed, leaving barley, oats and other large seeds. Indent cylinders work on a similar principle to disc separators. Impure grain is fed to the inside of a rotating cylinder. Seeds up to a certain size are picked up by the indentations and thrown into a trough above. By using two cylinders in tandem with different size indents, both smaller and larger grains can be separated from wheat. The scourer is used to remove any dirt adhering to the surface of the grain by beating them against the interior of a cylindrical wire cage. The dust falls through the cage and is discharged. Any remaining dust adhering to the grain is then removed by suction. The grain is now ready for milling. The aim of flour milling is to achieve the maximum recovery of pure endosperm with as little as possible bran and germ contamination. The crease makes it difficult to achieve this by stone grinding. Roller milling was developed in Hungary last century to overcome the problem. Roller milling involves three main stages: the brake system, which opens up the grain and progressively scrapes endosperm from the bran; the sizing system, which gently scrapes the bran from the larger endosperm particles; and the reduction system, which purifies and reduces the size of endosperm particles. Roller milling is greatly assisted by conditioning or tempering the grain. This involves first wetting the grain to raise its moisture content and then allowing it to stand for up to 18 hours. This toughens the bran, reducing its tendency to powder, but still allows the endosperm to fragment. Hard wheats are conditioned for a longer time and to a higher moisture content than soft wheats. The conditioning apparatus measures the grain moisture content and automatically adds the amount of water needed to raise the moisture content to the desired level. The moisture is added in a fine mist as the grain is augured along the inclined trough. It then rests in holding bins for the required time before milling. A thin curtain of wheat is fed to the first pair of brake rolls. The brake rolls are fluted or corrugated, and there are usually at least 4 pairs. Sieving tests are performed on the output from the first brake rolls, and the mill adjusted where necessary. Here we see the miniature brake rolls from an experimental mill. They rotate towards each other at different speeds. The fast roll rotates at 2.5 times the slow roll. Here we have slowed them down so you can see them. This is what happens when wheat passes through the first brake roll. And these are the first brake rolls of a commercial mill. Passage through the first brake rolls converts the wheat to a coarse meal. The meal is separated into 4 or 5 fractions by sieving. The principle is shown by this laboratory sieve. Here we have a vertical stack of 4 sieves. The openings in the mesh become progressively smaller from top to bottom. So the coarsest particles remain on the top sieve and the finest flour passes through the finest bottom sieve. In commercial mills, the sieving is done by a planned sifter. It works in exactly the same way as the laboratory sifter you have just seen, except that the process is continuous. The huge box incorporates a number of discrete sieving units, one for each grinding stage. After sieving, the coarsest fraction containing large pieces of bran with adhering endosperm is fed to the second brake rolls. These are closer together and have finer fluting than the first brake rolls. Finer particle-sized fractions include coarse endosperm or semolina, finer endosperm or middlings, and flour. The coarsest fraction after sieving the second brake output goes to the third brake. After passage through the fourth brake rolls, virtually all the endosperm has been scraped from the bran. The semolina and middlings from the planned sifter are further purified by machines called purifiers. These combine a series of sloping, oscillating sieves with an upward air current to separate fine bran and endosperm particles with adhering bran from pure endosperm. Sizing rolls with fine fluting are used to further purify the semolina and middlings from any adhering bran. After removing as much bran contamination as possible, the endosperm particles are progressively reduced in size by passage through a series of smooth or matte surfaced reduction rolls, sieving after each step. Flakes of endosperm, formed by passage through the smooth reduction rolls, are broken up by passage through pin mills or flake disruptors before sieving. The pins, rotating at high speed, break up the aggregates. The skill of the miller lies in choosing the correct blend of wheats to achieve the required flour specification, and in manipulating the properties of the flour finally produced by blending various mill streams. The degree of starch damage can also be adjusted by careful adjustment of roll pressures. Since flour commands a higher price than the byproducts of milling, the ultimate aim is to produce the maximum amount of white flour per tonne of wheat. The percentage recovery is termed the extraction rate. Its theoretical maximum is about 85%, the proportion of endosperm in the grain. In practice, commercial mills operate with extraction rates of about 78 to 80%. Not all flours are the same. Very different properties are needed to make bread, cakes, biscuits and pasta. Each product has its own unique specification for measures such as protein content, dough strength, water absorption, mixing properties, flour colour, and grade of wheat. The miller is assisted by cereal chemists performing tests on wheat and flour in the mill laboratory. Nowadays, the protein and moisture content are measured by near-infrared transmission or reflectance (NIR) instruments, which automatically calculate the protein and moisture content from the amount of infrared energy absorbed by the sample. The NIR protein test has replaced the tedious and dangerous Kjeldahl method, in which the sample was boiled with concentrated sulfuric acid and then with sodium hydroxide, converting the proteins to ammonia, which was recovered and measured. The farinograph is a recording dough mixer. It is used to determine the water absorption and the mixing properties of a flour. For bread making, high water absorption is desirable. The water absorption is the volume of water that must be added to a flour to yield a mix of given consistency. 500 units on this chart. The chart also gives a measure of the time taken for a dough to reach optimum consistency, the dough development time. and the tolerance of a dough to overmixing, the dough breakdown. The extensograph is an instrument which records the resistance to stretching of a sausage of dough. The measures of importance are either the maximum resistance or resistance at 5 cm and the extensibility. The maximum resistance is the peak height and measures the strength of the dough. The extensibility is the length of the base of the curve and measures the elasticity of the dough. That is, how far it stretches before it breaks. Moderately high dough strength is required for bread making, but not for biscuit and cake making. Flour colour is a measure of bran contamination. The higher the bran content of a flour, the darker the colour. Tri-stimulus colour meters are used to measure the colour of dry flour. The Kent-Jones colour meter measures the reflectance of a flour water paste. In the past, flour milling was more an art than a science. Today, flour milling is a highly technical process which depends on both the technical skill of the miller and the scientific skills of the cereal chemist.